Hi, statisticians. Today's lesson is on populations, samples, and data. Let's get started. As a high school student, you may already be receiving promotional mail from colleges encouraging you to visit their campuses, explore their programs, and maybe apply and potentially attend their university. This promotional material often includes data that showcases their benefits of attending their college, such as strong average financial aid, high salaries for graduates, high job placement rates, and good campus life survey results. But this raises the question, does the data you receive from colleges always point to the most accurate picture of what's really happening on campus? And that brings us to our key question for today. Can data about colleges be misleading? With that question in mind, let's move into our notes. We're going to discuss three topics today, starting with populations and samples. And as we dive into the topic of populations and samples, we are going to attempt to answer a big question that will motivate our course. Why do we learn statistics? To answer that question, I'd like to introduce you to Abraham Wald. Wald was born to a Jewish family in the early 1900s. He grew up in Hungary and earned a PhD in math. Before the start of World War II, he immigrated to the United States. However, much of his family was not as lucky. They were taken to Auschwitz concentration camp. During the war, Wald decided to join the Statistical Research Group, a group of mathematicians and statisticians who worked to solve problems related to the war effort. Now, it's worth taking a moment to think about what this meant for Wald. Members of his family were trapped in Europe. He didn't know what would become of them, but he knew that he would try to use his mathematical and statistical skills to tackle problems that, if solved, could bring troops closer to potentially saving his family. For Wald, every problem that came across his desk, every single one, was incredibly important, and we're going to investigate one of those problems today. This is the airplane problem. Many of the Allied forces bombers were getting shot down on missions. So the military made charts of the planes that made it back after flying missions, and on the charts they put dots in the locations where they found bullet holes. Then they asked Wald to analyze those charts and figure out the best places to add extra armor for future missions. Here is a particular example with 6 planes that came back after flying a mission over Germany. Now, keep in mind that armor is heavy, so you can't put it everywhere. So, using the data shown on the 6 planes here, if you were in Wald's shoes, where would you recommend they put extra armor? The nose, the main wings, the main body, the engines, or the tail wings? Take a moment to pause the video and choose your answer. When looking at this data, most people in the armed forces thought that the plane should be reinforced on the main body, the wings, the engines, or the tail, since that's where a fair number of bullet holes were found. However, Wald had a different answer. Wald said the nose, and I imagine everyone in the room thought he was crazy. The nose, there aren't any bullet holes in the nose on any of these planes. Why would we put extra armor there? Well, Wald's great insight was that, as we mentioned in the setup of this problem, that the military created these charts from planes that made it back from the bombing missions. This means that these planes could take hits everywhere that you see here, the main body, the wings, the engines, the tail, and still make it back. What we don't see are the planes that did not make it back, the ones that were shot down and could not return. And maybe those planes look like this, with shots in the most vulnerable area, potentially the nose. This was Wald's great insight during the war, to reinforce the areas where you see the fewest bullet holes rather than the most. This insight, which allowed the military to put extra armor on the most critical parts of their planes, helped the Allied forces to win the war. Statistics isn't just about calculating numbers. It isn't about finding means, medians, and modes. It's about thinking critically and thinking deeply about data. We call this statistical thinking. And if you can learn how to think statistically, you'll see the world in a very new and very powerful way. That's why we learn statistics. Wald's insight came from thinking statistically about populations and samples. A population is all items or individuals of interest. In other words, the population is everything or everyone. In this case, the population is all bombers that went on the mission over Germany. The population size, symbolized by a capital N, is the number of items or individuals in the population. For this example, the population size is 10 for the 10 bombers that went on the mission. A sample is a subset of the population from which the data were collected or measured. In this case, the sample collected by the military and charted were the bombers that came back from the mission. The sample size is symbolized by a lowercase m and represents the items or individuals that are sampled. In our case, among the 10 bombers that went on the mission, only 6 survived and came back to be part of the charted sample. So our sample size was 6. Thinking critically about how a sample is obtained is essential for getting good insights from data. For the airplane problem, knowing that the sample was composed of only the surviving planes completely changes how we think about the problem. It allows us to see that the areas with the bullet holes are the areas of strength, not the areas of weakness. This class is all about statistical studies. A statistical study is one in which data is collected from a sample in order to answer an investigative question about a larger population. In other words, we study a small sample in order to make inferences about a bigger whole. It's necessary to do a statistical study and collect data from a small sample when it's too difficult to collect data from the entire population. This brings us to our next topic, types of data. Imagine we collect data from a random sample of 3 students at our school. Here's the data we collected that describes those 3 students. Let's break it down. An observational unit is an item or an individual from which data is collected. For our example, the first student, Bill, is the first observational unit in our data. Each observational unit is represented by a horizontal row in the data set. To remember that we use the word row to represent a horizontal direction in a data set, think about rowing a boat with oars that stick out left and right. So when we're talking about rows, we're talking about the horizontal direction. A variable is a characteristic that varies between observational units. For example, one variable that we measured about each observational unit was their height in inches. Each variable is represented by a vertical column in the data set. To remember that we mean column in the vertical direction, think about the columns on an old building and how the columns stretch from the ground and up to support the roof. So when we're talking about columns, we're talking about the vertical direction. There are also different types of variables. A categorical variable is a variable that takes on values that are category names or group labels. Another name for these types of variables is qualitative variables. In general, the values of categorical variables don't have any inherent order. For example, take eye color. Data on eye color takes the form of categories like brown, black, blue, or green. These categories have no obvious order to them. No color is considered to be higher or lower than another. A quantitative variable is a variable that takes on numerical values. Think about quantities, hence quantitative. Another name for these types of variables is numerical variables. Generally, the values of quantitative variables have an obvious order. For example, SAT scores have an inherent order to them, with some scores being higher or lower than others. So an SAT score of 1600 is higher than an SAT score of 1000. There are also 2 types of quantitative variables. The first is discrete quantitative variables, which can only take on distinct sets of values. The second is a continuous quantitative variable. These take on any value within an interval. To get a better sense of what we mean, let's classify the variables in our student data set. First, let's look at height. What kind of variable is height? Well, height is a continuous quantitative variable. It has an inherent numerical order, with some heights being taller or shorter than others. So it's quantitative. Heights can also take on really any value on an interval, depending on how precisely you measure them. For example, with a very precise tool, you could measure Bill's height to be 72.3284 inches. Because it can take on any value on an interval, height is continuous. Dominant hand is categorical. The data in this group are not in any specific order. Left is not necessarily higher or lower than right, or vice versa. Number of siblings is a discrete quantitative variable. It has an inherent numerical order, with different students having more or less number of siblings than others. So it is quantitative. And we know that it is discrete because it can only take on certain types of values. In this case, you can only have a whole number of siblings. You can't have, say, 2.85 siblings, but you could have 2 or 3 siblings. Now, let's turn to shoe size. For this one, I would like you to pause the video for a moment and think about how you would classify shoe size. Okay, now that you've had a chance to think about it, let's discuss. So this is definitely quantitative, as there is an inherent order, with some shoe size being larger or smaller than others. But a more subtle part is determining whether this is continuous or discrete, since shoe sizes are not just whole numbers. In this case, Julius wears a size 11.5 shoes. However, it's actually discrete. Although people's feet could be measured as a continuous length, shoes only come in certain sizes. You could buy a size 11, 11.5, or 12. There's no such thing as an 11.3 size shoe. So that is why shoe size would be discrete. Finally, we come to zip code. Again, let's have you pause the video and think for a second about how you would classify zip code. Okay, now that you've had a second again, let's discuss. The values are numbers, so your first thought may be that it is quantitative. However, higher or lower numbers here don't necessarily mean that you could order them. They don't have meaning in terms of a number for zip code being larger or smaller than another. In fact, zip codes are labels related to locations. Another way you could think of this is thinking about finding an average. You could find an average or a mean height, but it doesn't necessarily make sense to find an average or a mean zip code. So in fact, zip codes are categorical. Even though they're numbers, these act as group labels for labeling regions across the country. They have no inherent order. Finally, let's turn to parameters and statistics. Parameters are numbers that describe attributes for a whole population. Statistics are numerical attributes that describe a measured sample. One way to remember these are that parameters describe populations. So P matches with P, and statistics describe samples. So S matches with S. When studying the whole school, someone might ask, what is the true mean height symbolized by the Greek letter mu among all students in our school? This is a question that asks about a parameter, since it is about the true mean height, mu, among the full population of all students at the school. The problem is, we might not have time to measure the height of every single student at the school, so it may not be possible to directly measure mu. Instead, something more feasible may be to measure the sample mean, symbolized by X bar, the symbol X with a line or a bar over it, among just the 3 students in our sample. In this case, if we calculate the mean height among the 3 sampled students, we get a sample mean of 68.1 inches. This value, X bar, is a measured statistic, since it describes only the sample of our 3 students. We can try to use this value of our statistic to make inferences about the population parameter mu. And a lot of this course is all about how to make those sorts of inferences. So more to come on that later. Now, let's turn to our discussion for today, which uses the concept we've learned to come back to that question from the beginning of class. Can data about colleges be misleading? This is a picture of Palo Alto College, a community college in San Antonio, Texas. In 2021, a student was applying to Palo Alto College, and he found this statement on the school's website. 89.3% of their graduates found full-time work or enrolled in their next level of schooling. Now, keep in mind, this is a community college, so both of these outcomes, finding work or transferring to a four-year university, are both considered to be good outcomes after graduation. After reading this, this student said, "This is great. I am definitely going to apply." However, I had a different reaction. Specifically, I had a suspicion that the 89.3% statistic might be misleading. So that's our discussion question for today. What might be misleading about this statistic? And here's a hint. Think about the airplane problem. So take a moment to jot down your initial thoughts, and we will discuss this question further in class. That's it for today's statisticians. We will see you next time.